Again, today's session is about from theory to practice, and we will be talking about how to master real-world simulations. I will have two, actually two presentations, to not only be one presentation. I hope we will have enough time for it. The first will be an introduction. This introduction will be talking basically about the industry. I'm an industry guy. I will tell you what is expected from your site to work in industry and to use the FA. Then I will walk you through some real world cases that I have personally used simulation to finalize my design. According to the introduction, so here is a quick background about myself. My name is Mohamed Hussein. I have my Bachelor of Engineering from Alexandria University in 2014. I have finalized the MBA, Master of Business Administration, in 2017, and I have finished my Master of Mechanical Engineering, which is specialized in static equipment, and FEA in 2021. I'm a CSWE for both CAD and simulations. I am user group leader, Solidworks, and Simolia champion. I got my certification as a TOT or train of trainer. It was in 2022, and I have delivered more than 125 training courses. During the first 4 years of my career, I have worked as a TA at my university. Currently, I'm working as a design engineer, not only a design engineer, because basically I am leading the static equipment team, which is specialized in static equipment designs and finite element analysis in our company. Here is a list of projects that I have used simulations, and here is the first point that I would like to highlight, that what we'll be talking about today is simulations. So simulation is not only depending on the software, but on you as an engineer. So what I'm saying today is valid for SolidWorks, valid for the 3D Experience platform, and valid as well for Simolia Abacus, if you are aware about Abacus, and even some other softwares. If you are, for any other reason, you have to use it, this you are going to apply the same procedures. I would like to start by revision log and what is how it started from my side. I started in 2017 preparing for this kind of material, and 2017 was the first revision. I used to review my content with many experts worldwide in 2018, 2022. Since 2024, I started to work with Matthias Robertson. I'm pretty sure that most of you is aware who is Matthias Robertson, and he's one of the coolest guys ever I met related to simulations. And he's doing almost the best animation ever. If you know him, if you don't know, please try to search for Matthias Robertson and follow him and check what he's doing on simulations. So we kept growing this content. We are updating this, I think, every year at least once, and this is what we have today. What will be the table of content? Basically, we'll go through an introduction to the finite element analysis. Then I will go to a very interesting topic, which is how we can perform manual calculations. And this point was a turning point in my career. It was one of the important points that why I am able to use finite element analysis right now in industry is basically because I am aware of how to do simulations in using manual calculations. And for sure, I'm not talking about the very sophisticated examples that I can do using manual calculations, but at least I am totally aware what the software is doing behind the scenes. I will go through workflow for SolidWorks. I will add another topic from a different presentation as well, just to add some reality to our presentation. So at any time, if you feel like you have any question, you can add this question in the chat. I will make sure to check it on time. And if you need anything, just raise your hand and you can unmute yourself and talk instantly. So what is finite element analysis? And first of all, we are talking about this introduction to the finite element analysis. So basically, our role as an engineer is to solve problems. And to solve problems, we have three ways. The first is analytical way to solve any problem. And what we are talking about, the analytical, is the basic equations that we used to learn and teach during our undergraduate. For example, I have a beam and I have some loads acting on this beam. So this is how it comes. So what is basically the limitation behind this analytical approach? If I think it comes to all of your minds that our real case or our real examples won't be that won't be that very easy or this very direct way. So you are right, it's not very direct, but in case you have this very direct problem, you can use your analytical approach to solve it. So what else I can do is using experimental. So if I have talking about this, you can set a full scale or even a scale, a small scale one from your problem, and you check what will be the behavior of your model or your design. Again, what we think about this, maybe some kind of limitation, maybe some kind of a lot of time to prepare uh, this setup, to prepare your problem for sure. And again, you will pay a lot of money, so it will be about the cost for doing this. And imagine what will be the case if I had any failure. I have to do it one more time after I do some modification to my design. So I will pay a lot of money, I will take a lot of time to finalize this design. So here is come to the third point. The third way is the numerical approach, and this is our topic today. What is the numerical approach? It's an approach that you can use some numerical equation. You can use your computer, you can use your PC, your laptop, or whatever you are using right now to solve the same problem. What I'm getting out of this basically is because the first analytical approach is only valid for some basic problems. For the experimental, it will take a lot of time and it will cost you a lot. But for this one, it will have less time for sure, and the cost will be reduced for sure. And imagine if I have any problem when using a numerical solution, I can just modify my model one more time and check what will be the updated results. So here is why this numerical solution is very important for us. When we checked when it started, and I believe the first research about it was 1956, and after 2000 we have more than a million of papers related to finite element analysis. This is just to let you know how it's a very broad way that is currently used for a lot of industry and applications right now. Talking about FEA in industry, and here is the best point or the most important point that we have to talk about. What about the industry? When we are working in industry, you have to know about that there are some tier of prevalence. What I mean by prevalence is which is more important that we have to follow. So first of all, when we are working in large industry, or you are working in a very large scale of projects. For example, we are working on power generation plants. We have to follow, first of all, the legal requirements. So, for example, if we are constructing a power plant generation in India, we may have, or for sure, we have some restrictions from governments that we have to follow. But if you are installing the same one here in Egypt, we have a different criteria. And if you are moving to USA or any other country, so you have to follow this criteria. Why we are mentioning this criteria while we are talking about FA, I will let you know very short. Another point that is equal is requirement. So for sure, if we have a owner, for example, like Aramco or whatever companies that is that will be using or developing this power plant generation, you have to follow this requirement. And here is tier one. Here is the first prevalence of documents. Second one is using codes, and one of the most codes that is used right now in pressure vessels is the ASME boiler and the pressure vessel codes. This is one of the most codes that is used worldwide for all static equipment and pressurized equipment, for example. And here is, if you went to this code, if you check this, you will find that there is a certain opportunities for you to use the finite element analysis. And you cannot use finite element analysis for everything. You have to check, first of all, if the legal requirements allowing you for this, the code allowing you for this. So it allows you to use the finite element analysis for certain cases, and in some points, it's not for everything. The third tier is about standards, and this is the most used standards, the API 650. This is for above ground storage tanks. The third or the last one, maybe like recommended practices. For sure, there are other documents, but here is the most important. We have, for example, this best practice for the API for the heat recovery steam generators, which is turned, I think, in 2024, in May 2024, turned into standard, not only best or a recommended practice. So why I'm mentioning all of this kind of documentation and what is the basic relation between them and between finite element analysis? Because of personal mistakes that I have done during my first or my early career days. When anyone comes to me and asking me to, we have a problem, we need to have a design for a certain product or so, I was initially thinking about FAA, but this was not the most accurate way, because I have to check first if the place that I'm going to install my equipment is accepting FAA. And if he accepts FAA, I have to check if he has a certain criteria for the person who is performing FAA. So for example, if you are aware about the FE, the fundamental engineers, and the PE, professional engineers in USA, same in professional eng or PEng in Canada. We have the same in Europe, like chartered engineer. There are a lot of certifications that you have to inquire. For example, to conduct a finite element analysis for pressure vessels, according to the ASME Section 8, Division 2, Part 5, you have to be a professional engineer or equivalent. So at the current time, if any of you performed this analysis, you have to check first if it's accepted by the code, if the code is allowing you to use if the code is allowing you to use the FA. So that was the first mistake that I have done, and I learned that I have to follow first the requirements, and then I have to check if codes if the code is allowing the use and what is the criteria for the person who is doing FA. So maybe now you are wondering that it's very limited usage of FA, but actually let's check this slide. What the design code can do for you is that, according to some equations, he can give you a yes or no, a pass or fail criteria. So, for example, if I am designing a pressure vessel under, let's say, internal pressure of 10 bar gauge or whatever the value, I have to use this equation to get what will be the minimum required thickness for a certain material. But what I can get is only a pass or fail. So if I used 10 mm of material, it will be okay. If I used, for example, 8 mm material, it will fail. That's it. But what about what happening inside this pressure vessel? Is it really unsafe to be used? Can we have any other criteria? Can we check what is the stress distribution in this vessel? Can we check under some local stresses, for example, like this picture? So here is that what the design code at this case cannot do for you. That's why we are using FE. FE here showing you what will be your product limitation, what will be the stress distribution, or what, or any other criteria that is requested for you or needed from even your client or even your analysis team to check what is happening inside this pressure vessel or any other equipment that you are using. Okay, so so far what we have checked is before taking the decision you need to check, is there a design code or a design standard that is recommend or a recommended practice, for example, that I can check to get the results I'm looking for. So if this is only the result you are looking for, if you are only looking for the minimum required thickness, you don't have to use FEA, or it's not only that you don't have, you cannot use FEA to get these results. However, if I'm looking for any other thing, if I'm looking for some stress distribution, if I'm looking for failure analysis, why this happened, what if, and a lot of other cases, at this case, I need to use FEA. Okay, so what are the steps for FEA? This steps is not only for SolidWorks, okay? If you are using any kind of simulation software or any simulation package, SolidWorks, 3D Experience platform, or Simolia Abacus, or even any other software, you will be following the same steps. So the first step is about the CAD geometry. So you have to prepare a CAD geometry that is being used, and this is why SolidWorks is one of the best software, because SolidWorks is the best in CAD. So you have already your CAD embedded in the same package that you are using for simulation. So first of all, you need to have this CAD geometry. So imagine that this is, for example, I have this geometry. Sometimes we have a very detailed geometries, and sometimes I cannot import it directly or use it directly in my FEA. So I need to do some sort of idealization, or this is only if necessary. So for example, here I am getting a simplified CAD geometry. If you check what is happening at this point, you will find that I have removed some fillets that is not needed and won't affect very much the results of my simulation. And just keep this point in mind, because I will get back to it shortly, and we'll check together how this will affect your final results. After you have your simplified CAD geometry, and in case you don't have anything to be simplified, you will be using your original CAD geometry directly. You need to define what is your study type, what is the material that you are using for constructing this part, what are the loads that are affecting these parts, and where it will be fixed, or what is the type of fixation that you are using, whether it's welded to any wall or ground, or what will be the fixation type. If you are working with assembly, you need to define as well an extra thing. What is this extra? Is about how parts are connected together. Because if I have assembly, some parts may have the degree of freedom to be moved. So I have to define how these parts are going to interact together. But in case you are working with a simple part like the one I'm showing right now, so you don't need to define any kind of connection. After this, you have your mathematical model, which is ready. This math model or mathematical model can represent only what is the material. You can see here I have defined the material, for example, AISI 1020 steel or whatever, or any other kind of material. I have defined as well, if you see this green points, or this green arrows, which represents the fixation points, and if you see this red arrows up, and this red arrows, which represents the force that acting on this. After this point, I'm going to the mesh step, and the mesh step is basically turns is this very big into small elements or small parts that are connected together and form this model. If you check here, this is what I have done after I have my meshing. I have FEE model, and finally I need to check what will be the results. So I have to do solve, I have to solve my problem and check my results. Right now, I have these results and I need to interpret my results. I need to check what I'm getting right now, what will be my product behavior, and I can get a set of results. So these 5 steps will be your steps every time and everywhere you are doing FA, you will be following this 5 steps. Moving forward, let's check about a manual calculations. So that was one of the most boring topics that I used to hear, and here is why I'm talking about it right now. It was during my master degree, and I was talking to one of my mentors, Dr. Ahmed Nagib, and we were talking that okay, he told me you are using the softwares very well, but you don't understand exactly what is doing or what is happening behind the scenes. You need to be aware of it. And during a course that I studied during my masters, I had a full course talking about what is happening behind the scenes. What has happened after for me is that I was totally aware about what is happening in the software. And even when some critical cases or some sophisticated cases that I don't know, I need to check it first. I need to check the effect out of it first before performing this. So I will be talking about this very shortly, in less than 5 or 10 minutes, before going to the SolidWorks. So I will use this example. So considering that we have a tapered bar, like you can see, what I mean by tapered is that I have a different cross section, W1 and W2, and W1 is around 2 inches. Don't worry about the numbers. I will use this file. I will send it to share it with you. So we have this tapered element. We have this one, and we have load acting right here equals B, and it's fixed right there. Fixed right there. So what is required from my side? Me, what is the material properties that I need? This is the Young modulus, this is the Poisson's ratio, this is the density, what is the yield strength, is the ultimate strength. So all material model and material properties that is needed for this model is given to you. And here he is asking me to define the nodal displacement. So what is the nodal displacement? You need to define as well forces, stresses, using hand calculations for 4 elements. So what is this? Let me take this snipe out, and if you see this, I have 4 elements right here. I have this point of fixation right here, and I have this in which the P is applied. So if I divide this into 4 elements, it will be looks like this. Let's say that we have 1, 2, 3, and 4. So we have 4 elements. If I decided to calculate what will be the surface area, you will find that here I have, for example, 2 inches, but the surface area here or the width here is less than. So I will do some kind of approximation. Can you see how this is different? In this example, he asked me to use only 4 elements. So I have element 1, element 2, 3, and 4. At each element, this is element 1, it consists of point 1 and point 2, 3, 4, 5. So I have basically 4 elements. However, I have 5 nodes. I have 5 points or 5 nodes. So here in node number 5, I'm expecting to have the maximum displacement. Here I have less displacement, less, until I achieve this point, which I'm expecting as it's fixed, it will have zero displacement. It will have a zero displacement. So if I decided to use four elements, I'm getting an approximation for the surface area, which is not totally correct. So maybe someone asking me, right, what if we decided to use the five elements, six elements, 10 elements, or whatever the number? So for sure, if you decided to use 10 elements, it can give you better results than using only four elements. So this is why I will go to this slide and imagine that we have a circle. Imagine that I'm asking you to draw some lines that will construct the circle. Someone decided to use these six lines, which represents the circle. If I try to ask you right now, how far or how close do you think this representation is good for the circle? We are all now aware that it's not very close. So, okay, another one decided to use more lines, which is better. Someone else decided to use more and more, else decided to use a lot. So, first of all, let me ask you, how many lines can be used to exactly represent the circle? If you decided or if you are thinking about this right now, so yes, thank you, Abdullah. It's infinity. So I will never do it. I will never have exactly, thank you, promise, thank God. I will never achieve 100% of the circle. That's and here is why. Thank you all for answering the question in the chat. Uh, that's why I will never achieve 100%. And here is the main reason from the first slides when I was talking to you about what is required for the FAA and why they are requesting that you should be qualified to use FAA and to generate your report. This should be by a very high qualified person because I will never get 100% out of the FA, and there will be some sort of error. This sort of error is you have to judge, you have to decide is this error is accepted or not, and there is no percent. Okay, so if for example I say that this is close up to 95%, is it accepted or no? You have to decide, and this reply will be different according to the application, according to the criticality. For example, if you are working in aerospace, it will be different than working in submarines, totally different than working in any other criteria, according to the application, according to the product you are designing, according to a lot of elements that should be taken into consideration. So here is the main reason why there will be still some sort of error, or at least I will not achieve 100% of exact results. So keep this in mind, and you should be aware about this one. I'm just using this example to illustrate how it's not very straightforward. So, okay, someone will say, but if I used only 6 lines, this is not good. But if I use 100 lines, will be better. So let's use as much as we can. Okay, I will get back to this when I decided to use, just to remind you that I decided to use only 4 elements, and I will move forward. This is the basic relation that I'm pretty sure most of you are aware about it. What is the average stress is force over area. You are all aware about this. What is the strain? Strain is delta L over L. And if you used Hooke's law, you are getting E times strain. Okay, this is the final results. So here, what I have done, that I am taking only one element out of it. I'm assuming there is an F, there is a force that is pulling this down, and I having an equivalent of K, or equivalent of a resistance force, is as if it's a spring that is preventing this from moving. So I'm getting an equivalence of A. This is represents the area. So whenever you made the assumption for the area, if you decided to use 4 elements, okay, but other one decided to use 40 elements, it will be more accurate. Okay. So this is the same one that we draw at the beginning. We have element 1, 2, 3, 4, and for each element we have 2 nodes. So I have a total of 5 nodes. And what I'm doing right now, or what I will be doing right now, is that I will check each node. For example, I have here this R, this is the reaction force, and I have here equivalent force downward until I achieve this point of B. So I'm getting this static equilibrium for each node. I'm not taking this into much details. You will have the slides and you can check it at any time. But this is what I want you to know right now, that we have all of the K1, K2, 3, 4, and we have 5 displacement, and we have the reaction force, and we have the pulling force that is acting at the very lowest point out of it. Okay, so when I'm checking here, I have this matrix. I will just rearrange my matrix, and I will go to apply my loads. I will go to apply the boundary condition. So when I'm applying my loads and boundary condition, it means that I am going to uh, replace this P with its original value, which is, I think, was 1,000. I will going to replace the U1, which is the very highest point, this one, because I'm assuming that this is a fixed point. So this point will be 0. And then I will go to apply the final. You can see here that as I decided to use only 4 elements, so here is my assumption. Here is my assumption. So, okay, I will get the numbers for each area, A1, A2, 3, 4, 5, and I will redraw it right here until I am having this matrix. This is the stiffness matrix, and I will solve them together. If you check this right now, I will be solving by the end total of 4 equations, and I have 4 variables, U2, 3, 4, 5. So I am able to get all of my variables. So I'm getting U1 0, which is basically one of my assumptions. Then I have U2. You can see it's for sure it has a value. U3 will be bigger. U4 and U5 will be the largest displacement ever from all of them. Okay, so I having them all right now. So here is, I solved 4 equations and I have 4 unknowns. And this is basically because I decided to solve this for only 4 elements. Now I would like to ask a question, and I would like to ask Prasad if you can allow is the first person who replies to any of our question on chat. If he so for the first one who replies any question whenever we ask, can you just give or allow him to get
Sure,
the
sure.
one of the voucher?
Sure, sure. Absolutely, absolutely.
Thank you, Prasad. So whenever we ask a question, the first person to reply will have a voucher from Prasad. Thank you, Prasad.
A voucher for
So
sure.
a voucher for what?
They will receive a voucher for sure, even if they have
Okay,
participated in the previous event.
okay. Uh, okay, so what I was saying is that I solved 4 equations and I have 4 unknowns. My question is, what if I decided to have 10 elements instead of 4 elements? how many unknowns and equations do you think I will have to solve? Okay, I think we have a lot of right answers. Okay, we have a lot of right answers. Okay, so your answer is correct. Most of you answered this in the right way. So I would like to talk to Akib Haider. So I think you said that only 9, but you have confused maybe between the number of elements and the number of nodes. However, the number of nodes equals the elements plus 1. Like what I have done here, for example, that I have 4 elements, I have 5 nodes, but 5 nodes. Okay. So when I have 10 elements, I will be having 11 nodes. And as long as I know the displacement of the first one, which is 0, I will solve for sure for 10 equations, 10 unknowns. Okay. So thank you all for giving us this reply. So just if anyone could take screenshot uh, from this one, and I would like to keep it right here. Why I would like to keep this right here? Just I would like to remind you of the numbers that we got from our manual calculations. Okay, this is enough for this part, for the manual calculations. Right now, let's go to FEA in SolidWorks. Again, I will use the same 5 steps for my finite element. So here is the first. What I'm doing right that I have modeled my model in FEA. I 2 inch, 1 inch. This is W2, W1. The length is 10 inch, and I have a thickness of 0.125. Okay. I can go to options, add-ins, and I can activate the SolidWorks simulations, or from that tab for the add-ins, I can activate SolidWorks simulation. After activating the simulation, you will find that now I have this simulation tab. I will get a new study. I can give it a name. So I name this as a static simulation, and I hit OK. So I have the model ready. This is the steps, almost same steps that I have talked about previously, that I will going to apply. So what I have done so far is only I got my geometry is ready, and my SolidWorks simulation add-in is activated. Let's proceed to the next point. After I have done so, I will go to apply my material. I will use apply edit material. I can search for whatever material I need. I can check here for the AISI 1020. I have these properties ready. I can search for the material. This is the same that you are using in your day-to-day SolidWorks and your everyday work. You can search for the material right here if you want to find any kind of material, AISI 304, for example. Here is the properties ready. But what if I couldn't find my material? I can come here and define my own material. I can define a new material. I can name it as whatever I want. For example, I can name it as steel. I can define my material model, and you'll find here that there is the first type of material, which is linear, elastic, isotropic, and orthotropic. I will talk to you about what are the differences between them. For now, I will define the linear, elastic, isotropic. If you remember from the first slide, I have all of this material properties ready. I'm
One
just
minute order ಮಾಡ್ತೀನಿ ಹಾಗಾಗತ್ತಲ್ಲ instead of 2 separate ones. Veggie paradise just
Prasad, are you talking to us?
Oh, I'm sorry. I'm so sorry.
Okay. No, no, thank you. So what I'm doing right now, I'm just defining my material. But I would like to take a moment back right here, and I will right now ask you another question. I will ask you another question. So if you check this material properties, you will find that we have some properties, for example, like this elastic modulus. This property wrote in red. However, if you check the shear modulus, the thermal conductivity, specific heat, they are all in black. And if you check some like tensile strength or compressive strength, you'll find that this is blue. So, for example, what do you think about this color coding? Do you think if what is meant by this red color, what is meant by the blue, and what is meant by the black? And let's start or asking only about the red one colors. Why they are marked in red? For sure, it has a meaning. Red are necessary. Can use this to find others because they are not required to do the simulation if they are red. Red for elastic region. Error. Anyone else can add more questions? Can can add more replies. They are a constant value. Okay, but I have the opportunity to change these values. They are material properties. Yes, Mamidi. However, I'm asking, they are all material properties. I'm asking why they are marked in red. Red because they affect simulation results. Let me ask you, Ashraf. Do you think that the blue one doesn't affect the simulation results? Red for interchangeable parameters, mandatory. Like this reply from David Yusuf Rabia related to stress strain diagram. Mm. Omar, red is necessary, black is not necessary, blue is important for some kind of result. I like this answer, by the way. I like this answer from Omar.
Okay, I'll note down the name.
Okay. Fact Muhammad Adil saying factor of safety. Prasad asking all of us to answer fast and correctly. Okay. Mariam is asking about the blue color. Abdullah, they directly affect material properties. Blue is optional. Yes, blue is optional. David, red is important. Okay. If we decided to move to this slide, here you will find your answer. All of the red market properties are mandatory properties. I cannot run my analysis if any of these values are not available, are not an input to the simulation. Okay, but what about the blue ones? The blue ones. The blue ones are optional. They might be needed for some certain cases, for some certain loads that you have added. So, for example, this tensile strength, this compressive strength, they might be needed only in some cases when you define, for example, factor of safety according to the ultimate tensile strength, you will need it if you want to define this factor of safety according to it. However, if no, so no, it's not required. This thermal expansion coefficient is the same as well. So you find that there is three properties marked in blue right now. Okay, so blue is not important, Osama. However, blue is optional. They might be needed or not. What about the black? What about the black ones? Like the shear modulus, thermal conductivity, specific heat, and damping ratio. No, they are not required for this type of analysis. Okay, they are not required for this type of analysis. Yes, thank you, Guzlan. Yes, it's not, they are not required. However, I have one last question for this slide only. We have another question. But if you think about the shear modulus, if you think about the shear modulus, do you think that the shear modulus is really not needed for the simulation? because I said here if it's marked in black, so it's not needed. However, do you think, according to your understanding in mechanical properties of the material, uh, that they are really not needed? Andrea, black not important. Black not needed. Okay. Khalid Mahmoud saying black not important. Muslani not it needs it not needed in simulation. Abdullah not no it's derived. Abdullah, what do you mean by it's derived? Abdullah Anas Khan, can you illustrate for me more? What do you mean by no it's derived? And Nerda saying no, it's needed. Ghazlan needed. Yusuf Rabia, it's not important. I missed some previous replies. Let's get back. I think it's needed. Yes, Kebrom, it's needed. Nihola saying no, it's needed. Yes, Omar Goha. I think you are Omar Gohari. I think we have met each other before. When you define Poisson's ratio and Young modulus, not important to redefine shear. Yeah, keep constant during this kind of simulation, so not important. I mean, shear need simulation. It can be calculated from value of stress strain. Okay. Needed. Yasin saying a relation between them. Khalid saying no, it's derived. Mary, if we need shear stress simulation, then automatically calculated from Young modulus. I like this reply from Tennessee. I think Tennessee, yes. Shear modulus is important. Yes. Z, yes. Because we have the design, the safe material efficient shear value. Okay, I can see there are a lot of good answers. Just for your very important information that the shear modulus, even if you added any value in this window, if you added a value, the software won't make any use of it because the software will use the values that you can see in my screen right now. He will use the Poisson's ratio, will use the modulus of elasticity to define this shear modulus. That's why I think who replied at the beginning about no, it's derived. So if you mean that, or if you meant that it's derived from this equation, so your answer is correct. I will let Prasad decide who will get this second voucher.
It's hard to decide. You have to decide.
I think it was Abdullah Anas Khan. I think it was this guy,
Yes.
Abdullah Anas Khan.
Yes.
Okay. We have another question. Don't worry. Okay. So right now, what we have so far, I have my CAD geometry. It was ready. I defined my material. Let's move forward. Let's define where exactly it's fixed. Let's add my fixation. So I will go to, and yes, let's stop here for a moment. So if you checked here, my mouse is on connection, and for your information, and because I am only using a single port, there are no connections. Okay, but imagine that I have two ports, for example, like my hands right now. I need to define: are they glued together? Are they are welded? They are acting as a one unit, or if any of them can left the other. So if my hand can lift right now, so I have to define another kind of interaction. But because I have here only one part, no need for connection. I will go directly to the fixtures. I'm going to the fixtures. There are many types of fixtures like fixed geometry, and here I like this point actually about simulation is about this GIF or this like small videos that is shown right here. It define for you what are the degrees of freedom that are restrained out of this. If you decided a fixed geometry, that means no movement x, y, z, no moments x, y, z as well. Okay, so there is no rolling. Sorry, there is no rolling. There is no radial movement. But if you decided to use this roller and slider, it's like wheels. They are like only roller and slider, so they can move only in one way, but they can't move to the other way. It's exactly like the wheels. If you have hinge like this one, if you even decided to move forward for some advanced, you will find we have a symmetry. If I need to add a symmetry between them, I have a cyclic symmetry. I can use a reference geometry to define my fixation in only one, two, or three directions. I can use on flat face, on cylindrical or spherical faces as well. If I have a symmetry, and here, for example, I can define a symmetry if I need it for this one. And I will ask you this question by the end, but yes, I may be able to use the symmetry for this model. This is a cyclic symmetry, and here are almost most of the types uh, of them. So I will use a fixed geometry, and I will define them this way. You will find this green arrows. You can change the color if you want. You can upscale them just if you wanted to upscale them to be very big. If you don't want even to show any kind of previews, so it's okay. If you want to change the color, you can do it. So I will hit OK, and right now I have this fixation. I can just add two slow clicks to rename, and I name this as a fixation. Here I have started to add a physical meaning to my CAD geometry. Started to add a physical meaning. Let's check right now after I define this fixation. I would like to define what are the loads, how this model is being loaded, how it's being acting on each part. I have a lot of loads. I have force, pressure, torques. I have centrifugal force. I have a lot of loads. I can as well import my flow or thermal effect from another simulation in SolidWorks. I can import it here, which is defined as a kind of, uh, let's say, flow destruction action, FSI. I choose here this face, and I will select the direction. If I wanted to select the direction, I can use it this way, and I will say that the value here is up to custom. But however, I need only to define a value of 1000 and only to reverse the direction to turn this into a tension force instead of pushing force or compression force. I changed the units to be inch, pound, second. So I'm defining this one right now as 1,000 of pounds, I think. Yes, 1,000 of pounds, and I will hit OK. So for now, I finished my geometry, and I finished as well the physical meaning, and I have this ready for my mathematical model to be introduced. What I will be doing right now, after I define this fixation, forces, material at the beginning, that I will hit a create mesh. Creating a mesh is like what we have done when we define the four elements. However, for this example, I will define a lot of elements. There are two types of elements. There is a high quality mesh elements, and there are draft quality mesh elements. I decided here to use a high quality mesh elements. And for your information, we never finalize a model with a draft quality. Sometimes I start with a draft quality mesh, and this is only for the very critical cases or the very big examples. I'm only testing what is happening. with the draft quality mesh, then I'm turning this into a high quality mesh. You will see here that we have three types of meshes: standard mesh, curvature based mesh, and a blended curvature based mesh. You have this ruler here which defines uh, the element size, and if you get this to the very left side, you are getting the worst uh, mesh size, and if you're getting this to the right, you are getting the finest mesh size. We have you can define this value right here, and you can see here is what I have got right now. Here is how it has been created very automatically from the software. I have this one. One of the most important points when you are dealing with 3D elements, and this is for your information, and you have always uh, check this. I just checked that there is Aya saying I can't hear or see anything. So can you just reply? Can you see me right now? Can you see my screen and hear me right now? If anyone can see us, can you
Yes,
just
we can. We can.
okay? Yes. Ali said, yes, you're asking about the H adaptive and P adaptive. I can give you an intro about this, but not exactly right now, but I can give you. Yes, okay. Okay, so when you have or when you're using 3D elements and you have small thickness like this, one of the most important tips and tricks is never define only one element through the thickness. Never define only one element through the thickness, or like this one. This is what you can see right now. I have only one element. At least you have to have three elements. 3 to 4 elements will be optimum, but 2 elements maybe okay. What I'm saying right now, this is only tips and tricks. This is like a best practice, okay? But we never use or accept this with only one element through the thickness. Here I can define a mesh quality plot. Quality plot will define an aspect ratio. This aspect ratio will show you what is the maximum aspect ratio. And what I mean by aspect ratio is, imagine that this is like a triangle. So can I use a pointer here, for example? So imagine that I have some. This is, for example, one, one. Okay, so if I have them all with the same length, so this is means the aspect ratio is around 1. However, if I have a very long side, okay, if I found this right here, so I have a high aspect ratio. If you have a very aspect ratio, that means that your mesh quality is not very good. Okay, this means this mesh quality is not very good. Okay, so we are trying to have mesh aspect ratio of around one. However, we are checking right here if what we have this, and what is the maximum that may be accepted is around 3. Is around 3 to 4 may be accepted, okay, but don't use like 10, 15 or whatever. And only count about the number. Sorry, don't only count about the number, but as well where exactly this one. So if this very bad quality element uh, is available on a very critical point, so you have to avoid use it. Okay, so I found here that this is the maximum one, and the maximum means this is the worst one. So I will check here this point. I will stop for a second. Again, we have this mesh element. We have this is the element size. This is the tolerance between them. I used a high quality meshes. You can see that I have around 1500 of elements. This will give you just a figure about the number of equations that need to be solved. I have a maximum aspect ratio of 6. I have a maximum aspect ratio of around 6, and I checked where is this 6. How many elements has an aspect ratio lower than 3, which is accepted for me, is around 95%. How many elements has an aspect ratio more than 10? 0. No aspect ratio more than 10. My PC used only 1 second to generate this one, to generate this mesh. Okay, this is the information from this window. What I will be doing right now is that I will generate a finer mesh. I will generate a finer mesh, and I will check what will be. This is the mesh appearance right now. I still have only one element through this. If you check this right now, first of all, I have 8,000 of elements. Previously, I had only 1,500. So how many elements that has aspect ratio less than 3? Almost all of them. But check the time that used to complete is 2 seconds. And it's okay to do this in 2 seconds, but if we have a very big model, that means what I have done right now is that I use the double the time. So don't only count about the time itself, but just try to have this represented with what happened previously. I will do more refinement right now. Can you see? Right now I have two elements across the thickness, and I have a very, very fine mesh. I have a very fine mesh. It's better, for sure it's better, but let's check this. This is the aspect ratio. This is the maximum aspect ratio. And I will check the details for one last time. What I have right now is that I used 4 seconds. It's double the time again. And I have, can you see this number? 54,000 of elements. Just imagine how many time would be used to solve this, comparing to the original one. Comparing to the original one. Was Danny right now saying, yes, it's better? I'm not sure if you are talking about this. Yes, now it's better, but you have to think first, do you need this kind of accuracy or not? Because for sure, I will be using a lot of resources to solve this example. So moving forward, I told you that you need to have two elements at least across the thickness. So I will introduce you to a point that is named as mesh control. So what is mesh control? Mesh control is when you need to have a better mesh in a certain area. So instead of just refining the whole model, you only refine certain points. And this is basically because I want to save my resources. I want my resources at least to be able to solve my problem. So right now, what I'm doing right here is that I am applying this size. I'm applying a very fine one to a certain size. So I started by the fixation phase, and I applied a very fine one. And I applied this as well here for the for the pulling force phase. You can see through the thickness I have a lot of elements, and it keeps getting larger to the global size of elements that we have. I define a better mesh across these edges, and let's check what will be the final results. Yes, okay. So instead of having this very fine mesh in the overall part, no, I'm having this right now in local uh, faces or local edges of the part. I'm checking everything and finalizing this by the to have a final check about this. So right now I have a good one, or let's say better one from the previous. However, I'm only having 14,000 of elements instead of 54,000 of elements. Instead of using 4 seconds, I'm using only 2 seconds. Last step is that I have to start running my simulation. To run your simulation, you need just to hit run. But I would like to show you here that we have two types of solver. I have an automatic solver. I have a manual option for me. So I'm choosing manual. I'm choosing between some sources, which are the direct solvers, and we have another for the iterative solvers. So if you keep it automatic, SolidWorks exactly using the best way according to your simulation. How he deciding this? He is deciding which is better according to the number of elements, number of degree of freedoms, and the type of loads and analysis that you are using. Right now, what I can see here is that I'm getting my final results. Let's change this units. I will check where exactly my maximum location, and my maximum location as expected at the lower face. I will change this to floating, so I'm getting this. I will go back to the definition. I will check inches, and yes, I'm getting this number. I will add more decimal places, and I'm checking the final results right now. If you see these results, and if you do remember, this is what we have got out of our manual calculation. It was 0.0053. What I have here is 0053. This is almost the same numbers. Correct. This is almost the same numbers. I can define as well what will be my factor of safety. I will define this according to maximum von Mises stresses or Tresca, for example. I will keep it automatic, and I will which defines this according to maximum von Mises stresses. Yes, and I have a minimum factor of safety of around 6.4 or 6.5. This is the minimum factor of safety I have across my model. What is the maximum factor of safety? It appears as well right there as almost 25. Almost 25. When you have this value, it uh, can give you some insights about which area may need to be uh, uh, more, let's say, more strengthened, or which area that has a lot of materials that you can get rid of part of it and provide some sort of optimization. I can get where is exactly the maximum stresses, and I'm expecting exactly the location for everything. Here is the maximum displacement, and I can generate this video animation for this one. I can save it as an AVI file, and I can have it. Okay, so that was a very quick introduction about the use of FE.
So basically today is continuation for what we started last week. presentation today is entitled as Building the New Monorail System in Cairo with Solidworks and Simulation. So basically, this is part of our work that we have completed at my company at Sweden Electric PSP. So I will start by giving you an introduction about what is the topic and what we have completed and how we have used simulation for this. I will skip this slide because we have already discussed this last time. But let's start by what are the takeaways from today's presentation. The first takeaway would be how we have simulated our structure during drafting. And during this project, it was one of a new lesson learned for me that uh, maybe I have completed my structure design, but I have to always take care of what will be the response during the lifting case. And you will discuss more, and I will discuss more about what is meant by the lifting case. Okay, second one is how, with the help of Dassault Systems experts, Omar Zohni especially, Dr. Omar Zohni, we have used the power of Abacus solver with SolidWorks models, and this is what is called the streamline the process from design to simulation. Okay, so today's content is about our company, basically an overview, what is the monorail project and what we have used for this. So I'm part of Sweden Electric. Sweden Electric is has a very inspiring journey. Started in 1938 as a trader in electrical equipment business and kept growing till today. In 2004, Sweden Electric PSP was established. Now we have 31 production facilities worldwide. Most of them are in Africa and with a presence in Asia and Europe. We have 48 international offices, mainly in Africa and Europe, and our products are proudly exported to almost all markets on the planet. At Sweden Electric PSP, we have five main business divisions: power generation and power transmission. We have water and wastewater treatment, mobility, and mobility is the reason why we are here today and what we'll be discussing now. And we have oil and gas division, our engineering department, which is divided into seven main sub-departments. We have over 250 of highly qualified engineers who serve all the previous mentioned divisions. And I'm proud to be part of the mechanical team at Sweden Electric PSP. So what is the monorail project? I will let you check this video. This is a word from our project manager. Uh, I will let you know more about this shortly. So, as you just checked, so Egypt is committed to provide more sustainable ways of transportation and easier ways for transportation in Cairo. And the monorail is one of the biggest projects worldwide that is currently under construction, and we are nearly from the official launch for public very soon. So let's start talking about what is the scope that we are doing as a Swedish PSP. So as a Swedish PSP, we are responsible for installing electrical wires and conductors on this beam. So starting by checking about this beam, and to understand this, we have an activity of installing supports each 3 meters. So this is the beam, and the beam is elevated on around 25 meters. So if you are trying to imagine what is meant by 25 meters, it's about you are walking in 8th floor or maybe higher than this 8th floor. So this line length is around 57 kilometers. So it's not able to do it with the regular construction methods. To do it, we have to provide a special type of cars that will be used for these construction activities. We have constructed the first type of cart, which is uh, what we are mentioning here is the mini cart, which has a weight of 2,000 kilograms, and it able to withstand around 500 of payload. It uh, it can weigh up to 4 workers, and it can work safely up to 8.5 meter per second of wind speed. This is the car, and the car is basically operated by electrical motor and powered by a diesel generator. We have all of these items that are designed and fabricated here in Cairo in our facilities. I will discuss more about these components lately. After installing these supports, we are moving forward to install the power rail. The power rail, or the conductor, which mainly provides the car's electricity. This power rail is a length of around 12 meters. So using the previous type of car that I just shown is not feasible, as this car is around 2.2 or 2.3 meter in length. So we have now a 12 meter of conductors that is needed to be installed. To do it, we had to design another kind of cart, which is the long cart. This long cart has an empty weight of more than 8,000 kilograms, and it can withstand up to 3,000 of kilograms with 8 workers and the same maximum wind speed for operation. So the length of this car is 16 meters. This car is basically driven with 2 electric motors, and we have a special side wheels. These side wheels are specially designed to withstand and to guide these cars during curves. We have this diesel generator, which is the power source for all of these items and auxiliaries. And we have this hoist. This hoist is basically uh, uh, to load and unload from the ground. So it will work while the car is on a 25-meter length, on 25-meter height on the beam. It will go down to the ground to withstand this around 1 ton or more, and weigh it up to this to the car. We had a lot of calculations that needed to be done. First is due to this instability that would be caused due to lifting from one side, and we have another calculation that we have to be done, and we have to design these side wheels for. I will discuss more in my simulation right now. So after finalizing this car, we had to design another one, the third cart, which is the short one. It's It has an empty weight of around 5,000 kilograms with a maximum payload of around uh, 3,000 kilograms, 6 persons as workers, and this is how it works. Right now, and after around more than 3 years of, I think it's more than 3 years right now, we have completely finalized, designed, fabricated, tested, and put into actions more than for more than 3 years, total of 24 cars. And in this picture, you can see around five of them are on it. Getting back to simulations, but this is a different type of simulations. And what we have done here is we have generated a game. This game is just an exe file that we are using and we used to deliver and learn and teach our workers about what they are going to face during their day-to-day work. We have designed this simulation games which describe the daily work routine, starting by the diesel generator operation and the area for the power rail, which will store it, moving down right here to this 15 meters platform on which the main job is being done, getting up here to this other side where we have the power and control panels. The card can move to both directions and each has a specific color on the control panel. For example, here you can see it in blue, and if I stop it and move it to the other way, you can see it in green. For safety purposes, there are six different places with 6 emergency switches on the card, which can immediately stop the card in case of any emergency. These hand brakes, which you can see it right now, these hand brakes must be all logged to enable the worker to move the hoist and start loading and unloading the power rail from the ground. So this is different type of simulations that we have done, and we have used it as a simulation tool for our workers before going. Moving from simulations and getting back to reality. Here is a video for one of the first tests that we have conducted on the cart. That was me, by the way. Okay, so getting to the real work, what we have done using SolidWorks simulations. Okay, so SolidWorks simulation was used for almost 4 reasons. The first was a validation and the verification of our structure calculations. So I can see that there is a question about, is this design done using weldments? So basically weldments, but weldments was only a part, because in this assembly we have, I think, or if I do remember right, it's more than 2,500 parts in this assembly. So first of all is the structural design. We need to check according to all of our loading cases how this part will react. And we need to make some decisions about having some points which is more, we need to empower some points, and this will be shown more next. We had to decide on the check how our structure will behave during lifting. So after finalizing all these cars, we need to lift them up to this 25-meter or so, just to make it on the beam. So what will be the behavior of this during this load case, which is not a regular load case? Sometimes we need to do some stiffeners, which is a temporary stiffeners only during lifting. Okay, only during lifting. So we need to design the wheels. Okay, we need to first of all sizing what will be the maximum reactions that each wheel will see, and we need to design this structure. We need to make sure that this structure will withstand this load. And here, what I like is that you can see a picture of the simulation beside a real picture of the final product. After finalizing this, and that was a part of our new scope that just arose during working. We needed to make something called gauge test. Gauge test. So all of this, we needed to use SolidWorks simulation. Okay, what is the structure design philosophy? Three main requirements. The structure has used the static simulations. Static simulations. You may be wondering, but this is a car. This is there. You should consider some dynamic simulations. You are right. You will check this right now. Structure design according to ECOB, Egyptian Code of Practice, and material properties that fulfill some of the project, or basically all of the project requirements. In this video, you will find this is the structure, and I will stop here for a second. Just after this. Yes. Now you can see that there is a reason, and if I try to ask you about where do you expect the CG, I will ask you, this is point 1, and this is point 2, this is point 3, 1, 2, and 3. So 1, 2, or 3. And we may ask Prasad if he can add more surprises.
I want to go with 1, but because I'm just going to go with 1.
Okay.
Okay, we have ones, a lot of ones, but some twos.
He will give some inputs right now. Okay, so we have these dimensions as shown, and everyone is free to add a new reply. One is for maximum force. I guess 1, 1, 1. Only says it saying
Says
2.
it.
Yes, says it. Okay, so here you can see that this area is around 13 meters. This length is around 13 meters. We have another top platform here with 2 meters, and the other platform on the other hand is around 1 meter. We have here diesel generator, which includes a tank that will provide this with required power, and we don't have anything here that has any weight. We only have some control panels, and so it's nothing compared to this one. So actually, only 1,000 is the correct answer, because due to this
Wait.
taller length right here, because of this taller length that we have. So, and we have another component that is a generator. That's why we don't have this CG in the middle of the card. I will just erase everything. Continue this video. Here is the diesel generator. That here is almost just the control panels. This sketch is drawn that is aiming to define where exactly will be the lifting lugs and the locations. So you can see right now where is the CG. Here is the center of gravity. Due to this unsimilarity, we need to have 4 different lifting lugs. 1, 2, 3, 4. I will open this lifting lug part. Do you think that we have drawn 4 different parts? Or do you think that I have modeled 4 different lifting lugs? Can anyone answer? Hello?
Guys,
my question is, as we just mentioned, we have
yes.
4 different lifting lugs due to the different orientation angle. So what I'm asking right now is that, do you think that I have modeled 4 different parts, or there is another modeling technique that I can use here to avoid modeling 4 different parts?
Yes.
Configuration. Thank you. Thank you. So configuration is one of my favorite ever. Thank you. Yes, this is one of my favorite ever SolidWorks hacks. I see. So yes, I have modeled it only once with different angles, and they are all here. Okay, going to how I may set up this simulation. If you do remember, yes, it's really one of my favorite tools. Okay, so if you do remember what we have discussed last session, that first you have your CAD geometry. So here, if you check the last one, I have a fully detailed CAD geometry. I have a fully detailed CAD geometry. This is what has been done for the long card and all of the other cards. Okay, so first of all, I cannot use this fully detailed. I have another configuration right here that is called FEA. I am naming this as FEA. So first of all, I have to do some simplification to this CAD geometry. I have to eliminate some of them. So Here I have some, I have grading. Grading is like the area where we have steel plates for people to move on. Okay, this grating does not affect the model, and I don't want to check any of the stresses on this grating. Okay, however, what I want to check is the stresses due to the dead weight of this grating. That will be yes or platform. Thank you. I would like to check what will be this, because there will be a heavy dead load due to this checkered plate, or due to this platform, or due to this grating. I need to check it. So I have used here something that is called remote mesh. Remote mesh. This remote mesh I have used for, yes, for 4 areas. I have 1 here, 2, 3, and 4. 1, 2, 3, and 4. 1, 2, 3, and 4. Okay, so I have used this remote mesh. I don't think that we have discussed this remote mesh last session. We have to define what will be the component interactions. These component interactions here are assumed to be welded, and this is not an assumption. This is what is happened in the real case. They are all welded. Then I have to move for the definition of the fixation points. Okay, definition of fixation points on in the case of lifting is not that easy. Is not that easy. Okay, so what we have done, and this is according to one of our previous work and one of papers that was published, we have assumed that this face, you see that I have splitted this face. I have splitted this face, okay? And I have, this is with a sin angle, by the way, that is directed to the point of lifting. So I have assumed this to be fully fixed, Okay, this is one of the assumptions that we have done. Then I have to do for the other one in opposite. I have fixed this only in 2 directions, only 2 directions. Same for the one in opposite. Can you see I fixed this for direction 1, direction 3, because for the third one or the fourth one for direction, it will be fixed for direction 1 and 2. Okay, so here I have defined what will be our fixation points. This is the 4 points that we have defined for this case. What else we have defined here? We have defined the gravity force, okay, and we have a lot of uh, cases. At that time, we had to define different type of loading scenarios, and this different type of loading scenarios has been defined in a different simulation studies. Why we have not used the load case manager in SolidWorks? Because at that time we didn't have this in our license. I've defined this wind loading, and imagine what is the case right now. We have these 4 points, okay, that is hanging the car, and we have wind that is acting this way. We have applied a lot of mesh controls, actually, and let's check what is our results. Okay, what we are doing is that we are studying and verifying our results across 2 different platforms. So if you do remember what I was saying during last presentation, that anyway you will have some kind of error. You will have some kind of assumptions that we have done, and we need to check what will be the final results. One of them, and or one of the ways that we are doing this on a platform, and then on a different platform that using totally different solver, and you are checking what are the output, what are our results. You can see here on the left we have this on the third party platform, and we got a maximum displacement of around 0.3 millimeters. If you check our SolidWorks results, we got almost the same results, and we have a 98% of similarity. We checked this again, but this one we checked for what is the maximum reaction that would act on our uh, fixation points, and these fixation points here are assumed for the wheels. So we check this, and we have around 5.6 of kilonewtons. So in our third party platform, we have a 5.9, which is around a 95% of similarity. Again, for different cases, we have 0.265, where we have 0.277, which is a 96% of similarity. And what we have here is almost 98% of similarity. Using all of this, we were able to be more confident about our results, about what we are getting of the software. We have 0.59, we have 0.6 right here, and we have, and this is a very good numbers, at least for our case and for our approval. This is, I think, was the last case, yes, and we have a 95% of similarity. What we finalized so far is we have agreed about what will be our structure members that we should use, and they are all safe. All stress ratios are fine for us. We have agreed about what will be our wheel reactions, and we have designed the wheel accordingly. So this is the maximum reaction at all the cases, at all of our assumptions, all of our loading cases, and we have proceeded accordingly. That was not everything. That was not everything. I would like to thank Dr. Omar. If I think a lot of you will be aware who is Dr. Omar. Dr. Omar Zohni has did some more advancing to this. Okay, so what he had with us right here is that he got this model. This is only for the structure model. Okay, and this structure model has been saved to the 3D experience platform. Then he has done a very fine mesh, very fine mesh, as you can see it right now. So almost ready from SolidWorks, but we have to use a more powerful solver. And here is what we name it in explicit dynamics. But if you checked any of cars, real cars in that you, if you're talking about Volvo or Toyota or whatever the cars that you check, all of them must encounter what is called a crash test. Crash test. Okay, so what is happening in crash test is we are taking the car, the real one, and trying to hit this car and check what will be the structure behavior according to this crash, in order to check what will be the stability of the car, what will be the safety for the passengers and the driver, and everything. For sure, we were not able to do it with only the use of SolidWorks, but we needed to use a more advanced solver like Simolia Abacus. Same approach has been done for the long one. You can see how this loads and stresses are transferred to the different parts of the car. I think you can see how these parts are getting squeezed. Can you see what is happening there? And how these parts are deflected more than this one. I'm trying to find a real world example for a crash test for another cars. So if you are able to see my screen right now, this is a crash test for 2024 Hyundai Ioniq. You can see what is happening and how this airbags has opened. This is for Volvo XC90, I think. Yes, this is Volvo. Mazda. So this is the idea of having this crash test. And doing this is something that require, first of all, a very, very powerful solver and a powerful computer to be able to do it. And what I'm saying here is this crash test has been done using the powerful of Abacus on the platform. So we're able to use a lot of uh, cores to finalize this. Okay. So that was the part for the first use case. We still have another one that we'll discuss, but I would like to have a break for 5 minutes or so to check all of your questions, to have any, if there is anything you would like to discuss before moving to the next ones.
There are a few questions, Hussein. One is,
Okay.
it's from Sumit. Have you performed a mesh independent study for getting mesh count? Can you tell me the best procedure to do that?
Okay, so first of all, for all of our simulations or for any simulations that we are doing, we cannot perform it and finalize this without having a mesh independency study. Okay, so this is first of all, we have to provide this. What we have done here, yes, we have done a mesh independency study for two reasons. First of all, that it's not only like a common practice or a requirements, but again, because for some points we have what is called stress hotspots. Okay, so we need to identify whether these points are stress hotspot or it was a real stresses. Okay, so we have done. What I'm doing right here is most of the time I'm doing this mesh independency study in a manual way. Okay, so in SolidWorks here you have what is called an H adaptive method. You have another one called a P adaptive, but with some limitations. And what I'm doing is I'm more aware about where exactly are the points of interest from my point of view or according to our design. So I'm always preferring to reducing the mesh size, refining this mesh size manually and checking what will be the final results. And we are always doing this as part of our final report. So I will never submit a report or a report to be proceeded accordingly without having this mesh independency study. And this is a manual procedure. Okay, this is it's a personal experience or a personal preferences that I am not. Sometimes I'm trying the H adaptive or the P adaptive, but I don't count on this automatic ways. Okay, I'm doing it manually. I hope I have replied for this question.
Yes, that was really brief, and I think it covered everything that the question had asked. And the second question is from Trevor: how do you know in case there is failure on a part?
Okay, so first of all, let's define, and this is it seems like an easy question. However, this is a very hard one. Okay, so uh, let's first of all define what is failure and what is factor of safety. Okay, uh, failure of the part is not only about the fracture of the part. Okay, let me try to illustrate it more. Uh, so imagine that we have this stress strain curve, okay, and pretty sure that most all of you are aware what is this curve, okay. So for example, one would say that having my model or my part or my structure that up to this point means that this is still safe. However, exceeding this will mean that this is a failure. Okay, so some people may define this. Okay, but first of all, this is not fully correct. Okay, so let's define it more. What is failure? Failure is when your model or your design cannot perform cannot perform its function. Okay, so when your model or your part cannot perform its function, that means this is a failure. Okay, let's talk about this area. This is the first part, which is called the elastic region. The elastic region, elastic. Okay, in this elastic region, whenever you are adding stresses, whenever the load increase, and then you remove this load, it backs to its original position. So, for example, I have this beam this way. I acted for, and I have done some loads or whatever, and the result was it became this way. But what happened after I removed it? After I removed this backs again to its original position. So like nothing has been. Okay, so this is in the elastic region. What if I exceeded this region and I moved to this area? This is plastic region, right? So what is happening here is whenever I'm adding a load, it never backs to its original position. It never back to its original position. However, it maybe have some deformation like this. So it never backs here, but it may be back in here. So let's think together. What if this happened? What will be the results to your model if we had this plastic deformation? Let's assume one of our latest crash tests. Okay, one of our latest crash tests that we have discussed. Okay, let me get this here one more time. If we stopped here for a moment and let me ask you, do you think that if we are only talking about this upper part, okay, this upper part, after this plastic deformation, do you think if this only the deformation happened, do you think that will prevent the car from moving? If this is only the deformation happen, do you think that will prevent the car? Not talking about this full crash or so. Only this has become this way. So if you try to move your car, it will still be moving. So if this is not a failure, this is okay. If this is accepted from your point of, not only your point of view, but according to your design. So first of all, sometimes we are accepting or we can accept that we are exceeding the yield point. We are exceeding, and in some designs and in many papers, you can see, yes, we exceeded this. However, our design is still able to function 100%. So how we define this? First of all, we try to avoid exceeding the yield point. But what if we exceeded the yield point? Does that mean that this is a failure? It's according to your design, and it's according to who will approve for you to exceed this point. So to cut it short, failure is according to your design. If you are only talking about this area, about this elastic region, about this linear area, if you exceeded this, sometimes most of the time we are considering this as a failure, or we are considering this as a not accepted results. Okay. However, that doesn't mean that this is a failure. If you check this, by the way, if you checked what happened here, this is a plastic failure, by the way. Some points here has exceeded the yield point, has exceeded for sure the yield points. But this is what we can say like a local exceedance right here, but this is not a global failure for the car. Imagine how many people has part of their car scratches, or part of their car that has a small crash or whatever, but they are still moving, and everything is almost fine. So I hope I have defined this, but because when we define the word failure, the first thing that comes to our mind that you never exceed the yield. But okay, sometimes if we exceeded the yield, that doesn't mean that we have a failure. Okay, that's it.
We have
I think that was the answer for the
yes.
last question.
We
I'm
have
checking
just
the
one more
chat.
question
Okay.
from Sajid. How do you select the design of the structure? Are you using trial and error methods to select the design?
Let me explore more. What do you mean by the structural design? I will let you know that we are a mechanical team, and we have another structure or civil team. Okay, so we are working together to provide these trusses and this system of structure, and we are checking using the FAA what will be the behavior out of it. but there is some sort of let's say some sort of uh, different ways to provide this structure, and we only using finite element to check what will be the final behavior.
There is one last question from Sumit Sarkar. Can we have composites other than general SolidWorks material, which you have explained last
Sure.
time? But yeah, I think they missed it.
Sure. There is a model here for composite material. You can define your own composite with the different layers and all the lamination and angles and everything. I'm not an expert in composites, but I'm totally aware about composite material, and yes, you can use it with some limitation for sure in SolidWorks, but it's available and you can use it whenever you need. And for anyone who is planning to check or to have the CSWE simulation, uh, you will find some questions related to composite material.
Wow,
Yes.
that's a useful tip.
Yes. If I do remember right, it was the first question. It was about composite material. Yes.
Wow. We have two more questions. Are we good to go?
Okay.
Okay. One is, can you explain H adaptive and P adaptive methods?
Can the P adaptive and H adaptive?
Yes, yes.
Okay. So let's get to here because I will for a moment stop this sharing screen and I will get to Okay, so let me reshare my screen. Okay, so that was part of what when I was learning this, and here we are talking about accuracy. Okay, so one of the first things that you need to check, and you always have to check, is about how accurate are my results. Okay, so for a given setup like this, I need to ask, is uh, is my mesh accurate? Yes or no? And by the way, it's not only that you are defining a more refined mesh, that means that you are okay and you are good to go. However, you need always to check it, and we never accept any kind of acceptance for any FA analysis without having this analysis. Okay, so what is the difference between H adaptive and the B adaptive? H adaptive means we have more number of elements. That's it. So that's why it's similar to having this mesh refinement with a manual way. So I'm just refining some areas, and I'm still using this way, and it's a very accurate way. So here is what is happening is that I'm checking this is the true stress response, and this is the response. This is the line according to the element size. So you can see that whenever you refining this, whenever this elements getting smaller, you are more capturing the results. Okay, so what is the difference between this and the P adaptive? The P adaptive, first of all, never changes the number of elements. So if you have used like 1,000 elements, they will keep as 1,000 of elements. What is happening once this for sure happens in the background is that they are using a higher order for uh, for aligning this. So again, uh, this black lines or this black is showing what is the true response. However, this blue one showing what is the response according to the element. So instead of having all of these elements, we can have almost half of these elements, but with a higher order, I can almost achieve the same number or the same, almost the same accuracy. Okay, so this is the basic difference between H adaptive and the B adaptive method.
That I think that answer was clear to the question. Thank you very much. We have one more question from
Sure.
Terence. When simplifying the model for FEA, do you recommend using developments and structural system or solid model for structural parts?
Okay, so for each question, I have to open a different presentation. Okay, I will stop my sharing for one more time.
All the unique questions.
Yes, but that means that all questions are really, really very interesting. It means that all of you are let me just try to open this one. I remember that was part of a presentation that was named 30 things in 30 minutes. Yes, that that was that one. Okay, so I will.
We can see the second screen, not the primary screen.
Oh, okay, okay. Uh, you can see this. So I have to stop it and I have to reshare for this one.
Yes.
Okay, thank you. So that was part of one of my first presentation. I think that was in 2022 in 3D Experience, and I was talking about 30 things in 30 minutes. I remember at the time it took me 40 minutes, not 30 minutes. And it was 30 tips and tricks about simulation. So one of them was how to select the mesh element types. So let's first of all define that less elements mean that you are solving your problem faster, but most probably less accurate. More elements means that you are solving this slower, but most probably more accurate. So what will be the optimum? The optimum is to understand the three different types of elements. First of all, the 3D solid elements. 3D solid elements. Second type is the 2D shell or membrane, and the 1D beam or trusses. Okay, so we have the three types of elements, and we have to decide which one to be used. Okay, so what are the differences? The truss elements is only for axial and torsional strength, only for them. Beam elements for strength in bending axial load. Okay, 2D elements for parts having a width to thickness ratios that is greater than 20. Okay, one of the most used cases is pressure vessels and tanks. Okay, 3D elements is whenever you cannot use any of the top three types, you go to the 3D elements. Okay, but one of the most things that I learned is that is this word or this phrase which mentioned it's not necessarily true that 3D elements outperform 2D elements or that 2D elements outperforms 1D elements. It's all about what exactly you want to capture. So I can get a better results with my 2D elements more than or better than the 3D elements. Again, I can get a better results from 1D elements as well. Okay, so you have to take this decision and just remember, because I was thinking the same way you are thinking right now, is it's okay, let's use the 3D elements for everything. So no, this is a wrong answer. 3D element should not be used for everything, and I will question why you have used 3D elements here, or why you have you haven't used 2D elements there. Okay, so trusses this way, same like the one you can see right now, it resists only axial deformation. Okay, whenever you have a tapered sections, you cannot consider this as trusses. Trusses is defined only by two nodes, and for each node there is a 3 degrees of freedom. So it's defined only by two nodes. Okay, that wasn't what we have used. Moving forward, we have beams. Okay, so beams is same trusses, however, it can resist bending, shear, and torsional loads. Okay, it can be a tapered sections, okay, but trusses cannot be a tapered section. So this way, yes, this can be considered as a tapered section. And if you decided to make it in a more refined size, you can use it like the picture on the right hand side. So okay, shell basically you have to be aware between the comparison of shell and membrane. Okay, for shell we have a 6 degrees of freedom, 3 for translation, 3 for rotation. You can capture bending stresses and the membrane stresses. Okay, but you have in plane as well as out of plane stiffness. The membrane is different. The membrane represents only the in-plane stiffness of the members, okay? And it has only 3 degrees of freedom, okay? When you fail to choose one of the previous elements, you are going to the 3D elements. So 3D elements are never my first choice. X elements are always preferred over tetrahedral elements, okay? However, if you are aware, in SolidWorks only tet elements are available. Tetrahedral elements are important for the transitions. Okay, whenever you are doing your mesh, sometimes you start with your default size and then you adjust to the required size that you are using. Use at least, this is, I think we discussed about this point last uh, presentation. At least you should have 2 elements across any thickness, but 3 to 4 elements are always recommended for these results. Don't forget to check what is the mass of your meshed body and compare it to the original body. Okay, you can do this mesh volume check in SolidWorks, and you can check what is the difference between what has been meshed and what is your original volume. Okay, so to cut it short and to answer your question, should I always consider instead of using beam or elements, beam elements or 2D elements, should I always consider 3D elements? No, it's never recommended. And just think about it. For such a model, if I can run this in like 6, 7, 8 hours, some of them it took us, I think, more than 18 to 20 hours to finalize this model, but this is for a single run. Okay, imagine if you decided to use everything in 3D elements, you would use 20 days, not only 20 hours. Okay,
Okay.
I hope I have answered
We-
this.
yes, we have more questions, but let's take them after the after the part, like, because you asked 5 minutes and the 5 minutes break went from 5 to 15, 20 minutes.
Okay.
So yes, I think for this question you have to open another different PDF properly. I mean, presentation properly. So
No. Okay. So what I can for you right here now is uh, this is another example in which we have used and we are currently using and evaluating how the behavior of our structure. Okay, so what we are talking about here is we are talking about storage tanks. Storage tanks are designed according to many standards. The most commonly used worldwide is API 650 standard. There is another European standard called EN 14015. There is another standard called AWWA. A lot of standards, so you have to choose which one you use, and it's sometimes it's not your own choice. However, this is according to your project specifications. So I'm illustrating here what we have done for our smallest size tank. Okay, so this is the smallest one. It has a diameter of 13.7 meter and a height of 10.25 meter. It stores around 1500 of meter cubes of liquid water. Okay, we have already designed and fabricated this tank. This, I think, was finished around 6 or 8 months back. We have already designed another one with almost 5000 meter cube and finished at the same time. Right now, we are designing almost 10th the size of this one, which is around more than 10 times the size, which is around 18,000 meter cubes. Just to be aware, it's around 36 meter in diameter. Okay, so it's a very big one. So what we need to discuss, or what we are using here, this is the structure of the tank. So you are doing some simulations, you are doing some calculations, and these calculations, basically calculations according to your standard, and you are checking what will be the behavior. However, we have to do some others that are beyond the this standard. Okay, because for the standards they are using what is called which is a type of the safety factors. And to use this, we are, or according to the standard, we have some limitation for that choice. But what if we decided, or what if we needed to know what will be exactly the behavior of our structure? We needed to perform this analysis. So we performed this to check what will be the structural behavior accordingly this way. Okay, and we have checked this, and right now we are studying a very small detail in each tank, which is has a very big effect on each of them. But why we are doing this, why it's very important to perform these calculations and this design for it, let's get back to one of the flood that happened in 1919. That was in USA in something that is called the Great Molas Flood. There, there was a tank. This tank was developed in uh, at that time, 1919, and with a very poor quality control. So there was some leakage that happened for this one. Due to this leakage, let's imagine what happened. This is the picture of this tank, and it has an 8,000 of meter cubes almost. That was the picture after this leakage. So it was a real flood. Okay, it there was around 56 kilometer per hour speed of this flood. It killed 21 persons, and there was 150 injuries. So just to let you know and to let you imagine how, you don't need to imagine because you can see two pictures for this tank before and after, for the area before tank flood and after the tank flood. So just to imagine that any uh, failure for this tank would cause a lot of injuries and would cause a lot of people that might be killed. So you have to check almost every single detail before taking and replicating this tank. Working with Matthias Robertson, we have developed this simulation. So you can check what will be the case if for any reason we have a very high head, okay, very high head uh, of water, of liquid, and at a sudden this head was collapsed like this way. If there is any structure, it will collapse it same like this way. And this is a simulation for what happened accordingly. You can see to the right what how was the picture at Boston in 1919 before, and how was the picture after this flood. So finite element analysis, FEA, is a very powerful tool, and you can see and you can check what will be the behavior of your model. You need to learn this way. You need to be aware about what happens internally in your model. Don't only count about a pass or fail criteria from your design code. That's a very important. You have to fulfill all the design code requirements, but you need to go beyond this. You need to go internally. You need to check everything in much detail. تمام. Check this. So I have a question here from Salah. He's asking about, he typed this in Arabic about this simulation, and he is asking if that was happened in SolidWorks simulation. No, SolidWorks simulation is not able to do this such detail, but however, this one was done using the 3D experience platform. So I think that was everything, and as I promised today that we have to finish before time, so we still have 9 minutes. We have almost 8 minutes, and we have a surprise to know from Prasad. Unless there are some questions, for sure I'm here if you want to ask anything.
Okay, I'll just reveal the first surprise. Many of you have missed out on our first session with Mohammed. I know you guys have missed out on the Solidworks certification. I know applying for the certification watches as well. So what I'll do is I'll reshare the form so that if you had missed last week, make sure you fill this right now. That's the first surprise. I mean, it's not a big surprise, but I'll just take it as a surprise.
By the way, it is because I received some messages from people who missed to fill this form. So I think just to say this right now, so this is very important. Yes, so thank you for this.
Yes. And we have some questions from our from our users. One is Mohammed wants to know the difference between contacts in SolidWorks simulation.
Okay. Basically, contacts in SolidWorks simulation is, and first of all, it's not only about SolidWorks, okay? Contacts in FEA, let's say it this way. So what is contact? And for example, what we have, let's go back to this one and check this. So what is contact? You can check this analysis right now. Contact is whenever you have a multi-body part or you have an assembly, not only a single part. So what we have done in our previous case, in our example last week, we had a single part, so we have not any need to discuss about contacts. But if you are doing any of our real world example, like what we have checked today, you have to use contacts. So what are contacts? Contacts is defining how different parts will act together. So for example, if I have this assembly and I have the outer shell, steel plates, and I have these structures are connected to the outer shell in certain points. So when they are connected, and they are connected as well to the roof plates, in a certain way. So, and by the way, I have a different contact way in this one. What is the first contact is assuming that they are welded. They are welded. Welded means that if someone has moved, the other one will move. Okay, so it's assumed like they are same part. Okay, so this is the first one. Okay, there is another definition is if they are not welded and but they are like this way. But what if my hand has moved up? If they are welded, they have to move together. But if they are not, okay, I can move this one. That means contact. So it's a physical contact. It's a regular contact. Okay. This is the same, by the way, for the roof plates to the structure. For the roof plates to the structures. Okay. So this is another kind of contact, and this contact is not that easy, by the way, and it requires a lot of processing time to be able to move or to separate these parts from each other. We have another kind of contact, for example, which is called shrink fit. What is shrink fit is whenever you are having something that goes inside another one, sometimes we are doing some heating just to have this to enlarge a certain area, and after it enters, it squeezes again due to the temperature difference. This is the shrink fit. Okay, this is a shrink fit. Okay, so we have. I think that these are the three main types of interference. We have interference that allows interactions between the models. I think they are these are all the main types of interference in SolidWorks and in ATA. What else?
Amazing. Okay, we have a few more questions. Where is it? Yeah, can we do simulations related to bodies subjected to vibrations? I mean, I think it's in SolidWorks simulation.
For sure. You have a full model here in SolidWorks for this vibration. You can define the natural frequency. We have a lot of questions about the natural frequency. You can check what will be the behavior of your model in case we have a certain vibration events. You can check this. You have a full dynamic mode here in SolidWorks. Yes.
We have one more question. Are interference fits in contacts as well? What? I'm not able to get it. Maybe our interference comes in contacts as well or not?
Again, I'm sorry.
Does interference fits, clearance fit and interference fits, does that count as contact?
Let's talk about interference because I'm not sure if, and I will answer, and just let me,
Yeah.
once I finish, let me know if I answer this according to what you mean. First of all, you are not able to perform a simulation if you have parts that are interfering together. Okay, you have interference detection mode in SolidWorks in parts and simulations, and you can check if there are any kind of interference, and you are not able to perform your simulation if there are any kind of interference. Okay, so this is the first one. Unless you have defined a shrink fit, interference, you will be able then to do it. Okay.
Okay.
So this is for the interference. For I have a certain mode in SolidWorks that I may allow model to get interfered according to a different loads whenever they are applied. This is a different point as well.
Okay. We have one more question. Is the
Sure.
exam hard?
I don't know, but
So it is hard if they don't know theory and just try to do the simulation as in just the software, I think. What do you say?
uh, you are right, Prasad. Is it hard? Yes, it's not easy. It's because finite element is not about software. Okay, it's about testing your real knowledge about FEA. And by the way, if you are talking about the simulation expert exam, there are 30 questions out of 40 questions. So you have around 60 marks, which is around more than, I think, 30% of the exam is all about some questions that you have to answer. You don't have to perform simulations or so. Okay, so in my opinion, FEA is one of the most advanced techniques. You need to be aware about a lot of things before performing FEA. So it's not hard. It's only needs a lot of practice. You need to be able to perform, or that you have already performed some simulations before doing this. Okay, so it's, in my opinion at least, it's different than having CSWE for SolidWorks and CSWE for simulations. There are some differences right here. Okay, because this is basically an engineering work. And by the way, when we have done this in SolidWorks, some of them in Abacus, some of them in 3D Experience platform, I have performed others in other softwares. All of them are almost, I'm doing the same steps. So yes, I may be faster in one software, but whenever I'm using another software, I'm just checking where is this option, how can I define poles, how can I define shell elements, how I can do it. So I'm searching for how the software works, but I'm not searching for the real or the real engineering information about it. So this is